Okay, so maybe it's time to start. Today we don't have our language 10, so we directly start the lecture. Yeah. Yes, in the Zoom, through the Zoom. Yes. So today's topic, the sequence-to-sequence model for speech recognition, or also call it end-to-end speech recognition. I will try to cover many of the speech recognition systems as much as possible in this the lecture, which is the first HMM-based the system that I briefly discussed last time, and then the other four the systems, the Connectionist temporal classification (CTC), attention-based encoder decoder, joint CTC attention, and RNN transducer. And note that the attention-based encoder decoder is quite the overlap with the machine translation. So if you guys missed some kind of concept, let's try to think about this problem to be interpreted as a machine translation problem, but just changing the source target to speech input. Okay, so before moving to the end-to-end speech recognition, I will briefly summarize what we have discussed in the previous section. This is, I call it noisy channel model. And how many people here remember in the HMM error, how to deal with this the speech recognition problem starting from the base decision theorem? I'm just curious because we used a couple of maths, right? So yeah, I hope you remember this the kind of a basic operation to make our speech recognition problem tractable based on some rule, product rule, and the conditional independence assumption. And by using this, we can make this problem. Oh, why it is not appear here? Let me try to. Wait a moment. Working now. Okay, cool. So we try to make the problem PW given O to be tractable by using the various probabilistic techniques, and then finally we tackle this the 3 distribution. This is a kind of the classical speech recognition techniques. And actually, this is not the end of the approximation. After that, we perform a lot of approximation for the acoustic modeling side. For example, we use a hidden Markov model, which is another way of the conditional independence assumption. And the language model, we also use the n-gram language model. This is also conditional independence assumption. And this methodology is very cool. With that, we can make the problem the tractable by tackling each of the small module rather than a big problem here. But at the same time, the method factorization and the conditional independence assumption actually brings a lot of the problems, brings a lot of kind of limitations for the model. This actually becomes a big barrier for making speech recognition to be improved. And mostly, again, comes from the conditional independence assumption based on hidden Markov model, n-gram, and so on. And actually, before we are working on the end-to-end speech recognition, many researchers actually try to kind of relax the condition or try to extend this model that comes from the conditional independence assumption. So this kind of the difficulty barrier is continued like 40 years or something like that, very long time. However, this barrier, this is a barrier, yeah, okay, is broken by sequence-to-sequence model. So now I will explain the sequence-to-sequence model and try to kind of deformulate a speech recognition problem based on the sequence-to-sequence model. And mostly the model is actually trying to directly model PW given O based on the single neural network. And again, as I mentioned, that this is not only in the speech recognition field. Again, machine translation or even other the processing field, sequence to sequence based single neural network is now replacing the classical the problem. So this is a kind of introduction of today's talk. And then now I will discuss about each of the sequence to sequence model. And the first is just review the HMM-based pipeline systems, and then discuss about the pros and the cons. So speech recognition is actually a sequence, one of the kind of typical example of the sequence to sequence problem. Input is of other speech features. It can be waveform or it can be the features, MSCC features, speech features, and so on. And then with a function to convert this the input sequence to the output sequence. In this case, in speech recognition cases, it can be a word sequence or a character sequence or other BP subword token sequence or whatever. And then the problem is how to solve this function. And then roughly, we have 5 ways to solve this problem. And I will try to explain one by one. And the first one, HMM-based speech recognition pipeline, which I mentioned already in the previous the lecture, composed of the feature extraction, this converting the waveform to the speech features like MSCC or log filter bank or whatever. And then after that, probabilistic approaches are making this kind of problem tractable. Acoustic modeling is the probabilistic model to convert the observation to the lexicon, the phoneme sequences, and the lexicon is to convert the phoneme sequence to the word sequence. And mostly this one is based on the dictionary. So the people may not use so much the advanced probabilistic models. But anyway, this part is also governed by the probability to some extent. And then finally, language model to providing the most likely sequence in terms of the word sequence. Okay, let's discuss about how to build this HMM-based speech recognition pipeline. I would say that this is not easy. So feature extraction part, mostly based on the signal processing. How many people here, for example, know the digital signal processing and so on? Not so many, right? Yeah, it's a little bit kind of still included in the computer science in some part, but mostly in the electrical and the computer engineering. And the acoustic modeling. This part is more like becomes computer science, but anyway, still the pattern recognition, machine learning, and so on is required for this acoustic modeling. Of course, some of the models is replaced with deep neural network. And the third one, lexicon. This part is more like a linguistics. And we get some kind of information from the linguistics. And finally, language modeling. This is more like the machine learning statistical model, NLP, and so on. So this to realize this kind of 4 blocks, we actually need to have a lot of knowledge. So I think it is very, very difficult to master all of these kind of areas and then making this kind of each of the block. By the way, I kind of simplify this problem. Actually, later, this one is fully combined, and then such processes happened. So then we actually have to also working on the discrete, the mathematics, the such, and so on. So to implement all of them, we actually require a lot of the knowledge for the various field. And I would say that even for me, it is very difficult to implement all of the components. But I can say that I have an experience of implementing feature extraction, acoustic modeling. Well, lexicon is more like getting some resources, but I have an experience of exploring that. Language modeling, I also have an experience of implementing the everything from the scratch with my kind of 20 years of the research history. However, I still have never implement the entire search process by myself. So like even for me, like experienced researchers, it is very difficult to cover the entire pipeline and building a speech recognition. And also, this is another important part is that this lexicon. This is the completely knowledge-based. Well, there are some combination of the knowledge and the statistical method, but mostly we use the knowledge. That is the pronunciation and so on. And we are lucky if we use the major languages like English and the Mandarin and so on. We could usually get to the very accurate pronunciation lexicon. But the other languages, it's more getting difficult. And due to that, it is really difficult to build ASR systems for non-expert. But end-to-end neural network is changing this kind of situation more. First, this is a single neural network to directly map speech signal to the target character. So since this compared with these 4 blocks, we just have a single neural network. So this actually greatly simplifies the complicated model building and decoding process. And especially this process doesn't have a lexicon component, which is learned based on the data-driven manner. So this means that we don't need a lexicon for, especially when we try to work on the new languages or some kind of new domains. We usually don't have a good, cannot get a good lexicon. In this case, actually, the end-to-end neural network may have some benefit. And the third one is, maybe I can also add moving back this one again. So each of the module is based on the different training criteria or different the criteria to optimize the system. So after we optimize each of the system and then combine the system, is it a global optimum? It's not. It's local optimum, right? Instead, end-to-end neural network potentially have an ability to globally optimize the entire neural network with a single system, single objective function. So this sounds like a very good benefit, right? But please note that these should be a pros and cons. For example, in some cases, we have a very good the lexicon comes from the effort, big effort from the linguist in some particular language. And we don't have enough amount of training data to fully optimize this the system due to the risk of the overtraining. And then, of course, the classical system is better. So this kind of property, I kind of emphasize it, but it can be a pros and cons. So please remember that. And I am now moving to explain about each of the end-to-end system. But one thing I actually want to admit is that usually we do not include a feature extraction as an end-to-end neural network pipeline, because we still don't have a good benefit of making this part to be represented as a neural network. MSCC seems to be very good enough and a very kind of a shallow computational cost, so that many of actually systems still are using the MSCC. So from now, I mentioned end-to-end neural network, but this is mostly after the feature extraction. Okay. So today we have a bit more time, right? Because we don't have a language 10. So maybe I can accept some questions here. Yes.
The difference in speech from other applications is that, yeah, when we're using neural networks, we still use certain feature extraction at the beginning. Is this more to kind of reduce the search space itself while getting the raw features, or does it have some other benefits as well?
Yeah, this is a good question, and it's the partly yes, the more like if we also applying this to the neural network in this the part as well, the network becomes very complicated, and even we have a more hyperparameters and so on, and it is the difficult to optimize, which is one thing, and the other part is that the front end part, feature extraction part, has a lot of requirement. First, it has to be very shallow computation cost, very small computational cost. It has to be the online streaming. It should finish the computation within a millisecond and so on. So due to this kind of a constraint, people still like to use the separate signal processing based approaches. But of course, this can be replaced like the 1D convolution with a very small window and so on, which is actually quite similar performance. But then what you mentioned would happen. The optimization becomes more difficult. And also training becomes a little bit more than using the feature extraction based on MSCC. So due to this kind of engineering reasons, mainly still people are using the MSCC here. Okay. Okay, so let's move to the first end-to-end method. This is connectionist temporal classification, CTC. This is historically one of the first the method, end-to-end method, the developed in the speech recognition area. And actually, CMU is one of the big contributor to develop this CTC based approaches. The open source software called Ethan is one of the first open source CTC tools developed here. By the way, for end-to-end ASR, there are a lot of kind of a CTC, CMU people that appeared as a kind of a main the developers, contributors, innovators. Yeah. Well, the other speech recognition part as well. So first, the CTC. I am always trying to use this kind of a figure, I mean, pipeline figure, so that, which model covers which the modules more clearly. So please note that. CTC is actually covering from the acoustic modeling to lexicon, but it actually doesn't explicitly cover language model. And I will skip the many of the kind of equations and try to give you some concept of CTC. So CTC, like the other the sequence-to-sequence the neural network, like encoder decoder, first we will do is more like an encoder to perform the feature extraction. The old days we use a BLSTM, but now it's replaced with the transformer or CNN and LSTM combinations, or the convolution transformer the combination. But anyway, the first part is to just get the kind of features, higher representation of the feature, which correspond to the phoneme or character or whatever. But the important part is that the output is character or text or token, whatever. This is usually very short compared with the input feature. And this the alignment problem is actually the difficult. And the speech recognition or even machine translation sequence to sequence model, the most the important part is how to deal with this alignment problem. And in CTC, we use dynamic programming. I will briefly explain with some cartoons about it. And the other property. Okay, the other property is that very simple. We have some, BSTM or self-attention or whatever, and then we just put the CTC loss, and then we can actually realize this the CTC-based speech recognition. This is also first, and this also be used for the online processing. So in this regard, CTC is quite powerful. However, in general, compared with the other end-to-end method, CTC is a little bit poor performance. And also the application is limited. I will explain about the meaning of this limited applications later. Okay, so I will briefly discuss about the problem of speech recognition, the major problem in the speech recognition, which is alignment. And as I mentioned, usually speech features are very long. This is say MSCC vector converted from this spectrogram. And then we have the C, like a character, 3 character. And the problem is how to assign each of the kind of a token, character, and the corresponding speech features. Maybe one possibility would be like that. Some of the beginning part and some transition of the spectrogram part, maybe first character while the consonants, yes. And then the center of the part, maybe second E. And the rest part will be the last character of the E. And is it true? Not sure, right? We don't know because we don't have such kind of label. Well, we are not sure whether we can definitely have such kind of a label explicitly. So it can be disalignment. It can be disalignment, little bit shifted. We are not very sure which alignment that we are taking in this problem. And actually, in this problem, can be well written, so-called trace structure. Let's say this is the SEE, the character, and I kind of reduced the input here from the more than 30 to the 5 for the simplicity. And the problem of this finding this alignment is actually try to find the path inside this trellis. And for example, one possible path can be go from this one to this one, this one to this one, and the final one. And this the path correspond to have the alignment of the first S is in the first 2 of the frames, and the second E is the third and the 4th frames, and the last character is the rest of the speech features and so on. If we know this alignment, we can actually somehow compute the probability. So with this the alignment, we approximately derived this the probability with the three the probability here. But then from here to here, we use a lot of aggressive conditional independence assumption. For example, this one S can be also depending on the other speech features 3, O3, O4, O5, but we ignore them. This E can be depending on the O1, O2, O5, or even this can be depending on this previous character S, but we ignore them. Same for this one, last one. So given the alignment, we also perform the conditional independence assumption. And then by using that, we can somehow compute the probability here. By the way, in CTC, there are little bit more tricks, like the so-called blank symbol is used to even use this kind of this one still has a different length. But by using the blank symbol, we actually have an auxiliary information to make the input and output can be the same length. But I will skip this discussion today. If you want, you can find some. You can find the reference that I am attaching later. And this is one alignment. It's possibly the other alignment. Again, still we can write it as a trellis. And then we can have this kind of alignment. And then we can have another possible probability based on this different alignment. And then finally compute this probability, we summing all possible passes. And this the summing all possible passes are actually very difficult problem. We need actually to compute the passes which can be possibly exponential. So this summation all over the possible passes are very difficult in general. But luckily, in this the particular structure, we can use a dynamic programming, and then can efficiently compute the pass, all possible passes, the summation of the all possible passes. And then by using that, we can compute this probability. And by using this probability, we can do anything. The most easy part is that, most useful part is that given this probability, we can use this as a likelihood training objective to optimize the model parameters and so on. So this is a kind of the essence of the CTC. But again, behind this CTC, there are a lot of interesting problem of how to introduce the blank symbols and how to introduce a conditional independence assumption, and how to still from this kind of the summation of all possible passes to get the derivative of the parameters requires some of the masses. And again, I will leave it to the reference. Okay, so I would like to discuss a little bit about the HMM that I have mentioned before and the CTC. So first, conditional independence assumptions. HMM CTC both are using conditional independence assumptions or not? Yes, they both using the conditional independence assumptions. And the CTC and the HMM itself actually doesn't have a language models. HMM, we can attach it based on the probabilistic the method, and the CTC as well. But the model, HMM model, CTC model itself actually doesn't include a language model like structure. And the use of pronunciation lexicon, HMM can do it because it has a clear the distinction with the lexicon model and the other component. CTC, it's actually directly predicting from the speech features to the token. So it actually cannot be easily combined by using the pronunciation lexicon information. And the implementation-wise, CTC is easier because this is just one model. Now I move to the attention-based encoder decoder. And yes.
You mentioned that CTC sometimes performs worse than some other approaches. Like what were you comparing it with?
Yes, this is a very good question. And this is actually with the attention or RNN transducer. This is because actually this part, as I mentioned, this part is actually not true. It should be conditioned on the other character, this one. But the CTC, to solve it efficiently, we ignore this character condition, conditional independence assumption. But this one is actually having a such kind of history of the text corresponding to including the language model, right? So that's why I mentioned that CTC doesn't explicitly include the language model. And this is a kind of a general case that the CTC would be CTC would perform worse than attention-based encoder decoder or RNN transducer due to that. Okay. Any other questions? Still have time. I tend to, how to say, make it longer, so I'm very careful about it. So next, the attention-based encoder decoder. And I will also explain the joint CTC attention because this is also used in our toolkit, ESPNet. And with default, actually, you guys are using this joint CTC attention in the assignment 3. So now the speech recognition pipeline compared with the CTC becomes different. Attention is actually including the language model as well. And this is because the attention decoder can also have a language model like behavior. Given the previous history of the predicted sequence, we try to predict the next sequence like a neural machine translation. And this part, like similar to the neural machine translation, again, the encoder is initially represented by the recurrent neural network language model, like a BLSTM or GRU, BGRU. But it is now replaced with transformer or convolution and transformer, the combination called the conformer, and so on. And here, I really would like to emphasize that it doesn't have a conditional independence assumption to derive this problem. So this, due to that, as I mentioned, compared with the CTC, theoretically and actually practically, the attention-based encoder decoder is better than CTC in terms of the performance. And also this structure is very, very flexible. Oh, I actually forgot to mention very important thing in the CTC. In CTC, actually, there's another assumption that the output length should be longer than, input length should be longer than output. So this is also another big constraint, which is very natural for speech problems. But like, for example, if using TTS, if we try to use the CTC for TTS, is this possible? It is very difficult because in general, TTS is opposite from the text input or phoneme input to predict the feature sequence, and the output is longer. And also the output is continuous, not discrete. This is another reason. But anyway, due to that, we cannot use TTS for CTC for TTS. But I am still trying to do it, by the way. I try to use the first discretize the feature. And then I also try to kind of upsample the text and making it longer, and then apply to CTC, but it didn't work. So if you guys are interested in, you guys can try it as a research the project. Yeah. So then this is actually one other comment. Some people may fail to train your model in the assignment 3. Some cases, this is because your model, your data may not satisfy this condition. Speech features, input features should be longer than the output, the labels to perform the joint CTC attention. So in this case, your training is failed and doesn't output the meaningful result. And if it happens, CTC probability becomes none and so on. So in this case, instead of posting question to the Piazza, I recommend you to check the data. Speech features almost all the cases longer, must be longer than the text. So in this the case happens means that your data preparation is wrong. Okay, sorry about that. I just remember the one kind of important note for the assignment 3. Okay, so this is the reason that attention-based encoder-decoder has a wide applications, because attention-based encoder-decoder doesn't have such kind of limitations. It can be used even the output, the sequence is longer than the input. So we can use it for the TTS as well. And we can use, of course, it is originally developed for the machine translation and so on. And the nice part is that because the alignment part is very flexible. It doesn't have so much constraint, but it's actually this flexibility sometimes becomes a difficulty of making training the attention-based encoder-decoder. So I will try to explain a bit more about the attention part. This is more correctly, we may call it source target attention, because we also using a self-attention. So self-attention and the source target attention is different. So please remember that. The source target attention is to convert the input features to the output context vector by using the weighted summation. That's it. There is no constraint except for that this one is a probability. And with this kind of flexible architecture, it can be used for many of the applications, as I mentioned. How it looks like, let's say, alignment pattern that I mentioned before. In the previous cases, I kind of hardly assign, like for example, this area to be a first S, and this area to be the second E, and the third part will be this area, and so on. I hardly assign each feature to the corresponding the text. And then the path is actually probability. However, in the attention cases, the attention weight is actually already soft. So in the first the character S could have a higher probability in the previous 3 other frames, and the next the token can be more higher probability in the next chunks of the frames, and the last of the frames can be can be more have a higher probability in the last chunks of the speech features. So it's slightly different. Previously, we considered it as a hard alignment, but now it's considered as a soft alignment. And please note that even this person has a connection to all the kind of the features. It is very low probability, but it's possibly it happens due to the mathematical constraint. And then the attention, source target attention can be written as this kind of picture. Well, we can also write the previous, the hard alignment as also based on this kind of picture. And the soft alignment can also be usually written as depicted by this picture. And then the higher probability means that this token attend this region of the speech features. And generally, I want to note that it becomes diagonal. This is actually very important, the property in speech. For example, do you think the token, end of the token here would be depending on the initial part of the speech features? There might be small probability, but mostly no, right? Same, the second the token should have the higher probability in the second region of the speech features. And this the property of input, the sequence and output sequence, the correspondence has some kind of keeping the order. It's called the monotonic attention. Due to that, it's actually the attention weight is written like this one, the line. By the way, this monotonic attention is important for speech, or the important speech recognition, or important for the speech synthesis. But of course, it doesn't have to be in the other sequence-to-sequence model, right? Like a machine translation, the ordering happens. Ordering happens, so that we actually don't have to force this monotonic alignment property in the machine translation. But for speech, this is very important. And this is a kind of one very typical wrong alignment. And this is a reference and the corresponding the attention-based result. And the blue line shows that it's actually the errors. What happens? This one first, do some kind of the attention monotonically, but suddenly they actually switch back to the beginning of the token, and then started to the same things again. And this the patterns they appear the additional 2 times, and it's actually corresponding to the very large insertion errors. And this naturally happens in the attention-based encoder decoder. And there are a lot of ways to avoid this kind of approaches. For example, by limiting the output length and so on. So this is a kind of a way to avoid to have a wrong alignment due to the too flexible the alignment. Yes.
So, also can we add like a regularization for the output length to?
Yeah. So there are a lot of ways to solve this problem. First way is as I mentioned, setting the length a priori, because given the speech features, we could expect the length. The other way is to see the attention weight. Do not attend the same part twice or more than twice, or the more specifically accumulated weight should not be higher than some threshold and so on. And the other solution is I will explain the CTC, the joint CTC attention. Okay, so now I will also discuss about this the 4 part And we mentioned about the difference with the CTC, HMM, and attention. The first part, conditional independence assumptions. Now, attention actually does not have a explicit conditional independence assumptions. So this is a kind of a unique compared with HMM and the CTC. The other part, language model. And as I mentioned, the attention decoder network implicitly has a language model. So that it actually can have the language model like behaviors in the decoder, which correspond to improve the performance from the HMM and the CTC. Although HMM and the CTC, we can also combine the language model. So finally, the performance may be comparable. But if we purely compare it with the HMM, CTC, and attention has a benefit. And the other two are very similar to CTC. The attention is also direct mapping. So it doesn't have a lexicon information. So we cannot use the lexicon information easily in the network. And the implementation compared with the HMM, the lexicon, language model, FST-based approaches, attention is still easier. CTC is a bit further easier, but attention is still easier compared with the HMM. The last, not last, the third one is the joint CTC attention. This is actually try to solve the problem of the attention weight, because this attention, the flexible the source target attention was very annoying issue when we don't have so much computational resources to tune the parameters, or we don't have enough data to train the attention-based model and so on. Due to this motivation, they actually this first author, Soo-Young Kim, is also the graduated from here. And when she was an internship student with me, when I was in the company, we actually developed this approach called joint CTC attention. The idea is simple. CTC has a monotonic attention. The attention doesn't have. So how about combine these two methods? And how to combine? We just using a multitask learning fashion during the training. We actually attaching the attention-based encoder decoder loss and the CTC loss to regularize this network to be monotonic. And even in the output, we actually combine these two results because CTC also do the speech recognition, attention also do the speech recognition at the same time. So why not combine it during the inference? By doing that, we actually can solve the attention, too flexible attention patterns by using the help from CTC. And the assignment 3, people are using the ESPNet. And the ESPNet are using this joint CTC attention as default. And this is a kind of an example that I showed before. This attention pattern is not very good. We just have our same attentions the 3 times, which is well regularized based on the CTC constraint. And then we recover the monotonic attention.
What are the axes here?
Yes. This is the output, and this is input.
So these are like corresponding to the void indices.
Yes. Yes. It's actually in this case character in Chinese. So. And this is another very good, very kind of the frequent example of the failed attention. Attention stop to attend, and then only the output character, the output only output a label that the before reaching to all the kind of consuming all the features, and then this corresponding to become the deletion errors. And this is also can be well recovered based on the joint CTC attention. So joint CTC attention is easier to make attention tractable. So that's why we use it as a default. But this is just makes it easier. If we have a more the tuning and some other effort, we can still make attention to be working like other people are doing. Okay.
So will this also happen if the downsampling is a lot in the network, the deletion error?
Yes, downsampling a lot, and then we don't have enough information to get the kind of the output token, and then this may also happen. But if we correctly downsampled, I think still the enough information will be gone to the encoder output, and then this kind of deletion would not usually be happen. But if we have aggressive downsampling, yes, the deletion errors still happen. Okay, so the last part, RNN transducer. This is actually one of the most widely used the neural network end-to-end system now, especially in the industry. And this approach is actually quite similar to the CTC. However, the method is try to kind of relax the conditional independence assumption, especially for the label part that I will explain in the figure. But anyway, the RNN transducer based approach is it's also handling the language model like architecture based on this kind of neural network. And then this part is very similar to CTC. By doing that, we can keep the CTCs the benefit like the simple and the explicit alignment based, and also it's very good for the online streaming system. While it's actually also still lower than the lower performance than the attention based on the still there are some conditional independence assumption. Also, the RNN transducer takes over the CTCs, the issues, which is it's only applied to the case that speech features are longer, input features are longer than output. By the way, it's actually technically RNN transducer can avoid it by using the very kind of a cool transition method, but practically still better to have longer input features than output features. That is based on my experience.
Explain the transition. What did you just say that part?
Yeah, I try to explain that. So this is that kind of a trace that I mentioned before. And if we have this kind of a loop, right? And then, as I mentioned, in CTC, we actually having the very aggressive conditional independence assumption to remove many of the kind of conditions and then compute this probability. RNN transducer actually slightly modifying it. It's keeping this condition here, a condition here, so that it actually also holds the dependency of the history is corresponding to the language modeling. So in this sense, this behavior is very similar to the attention-based encoder decoder in the sense that it's including the language model. However, still from here to here, it has some kind of conditional independence assumption in the input feature level. So that actually slightly the transducer is performing worse than the attention-based encoder decoder in general. But the nice part of this the RNN transducer is that again, we still have a kind of the consider history of the token, output token, and relax the conditional independence assumption from the CTC. And also this one, luckily still we can compute the all possible summation of the all possible paths based on the dynamic programming. Okay, so this is a kind of a very, very last part of the HMM versus CTC versus attention versus RNN transducer. And again, conditional independence assumption like if we consider this one, HMM and CTC are very aggressive. Attention almost doesn't have explicit the conditional independence assumptions. RNN-T has some conditional independence assumption, but compared with the CTC, it's actually more relaxed than the CTC. And the language modeling, attention RNN transducer, including the label dependency in the model. So it actually can hold the language modeling like behavior. But all three methods, CTC, attention, RNN transducer, cannot well use the lexicon model because it doesn't have an explicit module of the lexicon information. And finally, implementation. Again, compared with HMM lexicon language model, it is still easy. So that's a kind of a comparison of this kind of a four method. And finally, our quickly summarize all the kind of five methods. And except for the HMM-based pipeline, actually the ESPNet assignment 3 has all implementations. Default is number 4, joint CTC attention. But by setting the some kind of hyperparameter, we can switch to the attention-based encoder decoder, or we can switch to the CTC. Also, by changing the configuration, we can also apply the RNN transducer. And someone, if you want to play with this one, or if you want to kind of improve the performance, based on the other architecture and so on, you guys can actually play with this form implemented in the ESPNet. That's the yes.
You mentioned your joint CTC attention model.
Yes.
Since both CTC as well as the attention-based encoder decoder does language modeling separately, right?
Mm-hmm.
So how do you combine the outputs of the language models together? Do you just take the maximum of either of those cases?
Yeah, very good question. It's actually performing the first the attention-based encoder decoder. We use the beam search, and during the beam search, we actually combine the score of the comes from the attention, comes from the CTC, or even comes from, by the way, external language model and so on. Yeah, this kind of score combination is performed during the beam search. That is another actually trick of the making the joint CTC attention performs better than CTC or the attention-based encoder decoder. Yeah. Any other questions? So if not, let's move to the discussion. And today's discussion is please talk about assignment 3. Your experience of what part is difficult and what kind of tips are the important for the other people, and some other configurations like what kind of GPU you are using and so on. It could be a good information for the other people as well. So please try to describe it. So that's the today's discussion. So let's move to the discussion.